let's go to the next talk. It's by Vasilisa Nikiforova, and she will speak about torsion by gravity. Please.
Yes, thank you very much. I'm very glad to be part of Quarks. Let me share my screen. I will talk about torsion by gravity today, which is the thing I'm working on, and it's a purely geometric theory of modified gravity. And I suppose that not everybody here knows well what is torsion by gravity. So let me remind you a little bit shortly the basics. So Eli Carton say that it's too restrictive to set torsion to 0 and to consider only the Levi-Civita connection. So he said, let's consider torsion or torsion full connection being independent field, independent from matrix. So we have two bases. We have a matrix and we have torsion, and there is a link between matrix and torsion, which is called metric compatibility, which consists of the fact that the covariant derivative of the matrix is 0. Or, which is more convenient to work in my case, we can say the same in terms of moving frames and connection form A. So when you will see the letter A in that follows, it is a torsionful connection. And we can define a curvature F on the base of this torsionful connection A. And the simplest theory, which is based on this new type of geometry, was the Einstein carton theory. Einstein and Carton never really worked on this theory together, but they had similar ideas. But this simplest theory has no interesting conclusion, because it is equivalent to GR in vacuum. So torsion does not propagate, and then it is not very interesting. And the question appears whether we can construct a theory of propagating torsion to awake torsion somehow. And this is precisely torsion by gravity. Here you can see the main points in the history of appearing of this theory, starting from the papers of 80 and 81 up to the paper of me and Thibaut Damour, where we at first time use the notion of torsion by gravity. So what it is made of? To construct the Lagrangian of torsion by gravity, we take the Lagrangian of general relativity. We take the Lagrangian of Einstein carton theory. I remind you how it looks. It is the same as in GR, but instead of curvature R, which depends on the metric, we use curvature F, which depends on the torsion full connection. So we take these two parts, and also we take some square terms of Ricci tensor of the torsion full connection A, up, up, and up. So you can see this is GR part, this is Einstein carton part, and this is a square part. I remind you that F means curvature of torsion full connection. So we have such a Lagrangian, and you can see immediately how many parameters are in the Lagrangian. We have a G0, which is a strength of a usual massless spin-2 interaction. We have eta, which is strength of massive spin-2 interaction, and we have kappa, which is range of massive spin-2. I will explain it later. We have also C34. So we have a 4-parameter Einstein carton type theory. And I already said, but let me repeat, the field content around flat space is massless spin-2 and massive spin-2. So we have two particles. One of them is massless, one of them is massive. So it's such an interesting mixture where general relativity and Cartan's idea twisted in this way that it gives a kind of bigravity. And since this is a bigravity, let me talk about it in comparison with the most well-known and established theory of massive spin-2, which is biometric gravity, ghost-free biometric gravity. So let us compare these two theories. I recall you that in biometric gravity, the main fields are two matrices, G and F. We have Lagrangian, also we have a massless spin-2 particle and a massive spin-2 particle. In biometric gravity, both massless spin-2 and massive spin-2 are some combinations of the perturbations of these two basic metrics, G and F. While when we look at torsion by gravity, the main fields are metrics and torsion, or torsion full connection, it's the same. We have such a Lagrangian, which you already have seen, and both massless spin-2 and massive spin-2 excitations are some combinations of metric perturbations and the perturbations of the curvature f, as you can see here. And concerning ghosts, of course, biometric gravity was proved to be ghost-free around generic backgrounds. While here, what we achieved at this moment is to prove that the torsion by gravity is ghost-free around the flat space, around Einstein spaces, and around the static spherically symmetric solutions. At least already something. So let's continue. Here you can see explicit field equations. I just show it to you. So on the right-hand side, we have sources for metrics. It is C mu. For torsion equation, it is spin density. And I would like to point out that these equations are only second order in connection and metric, which is remarkable. I will just mention that before we considered a theory which is a little bit wider than torsion by gravity. It had 5 parameters, and we tried to study self-accelerating solution to explain the modern acceleration of the universe, but we found bad instabilities, so we did not explore it more. And then, when we come back to the torsion by gravity, let's see which phenomenological consequences does it give. Let's look at the world of torsion by gravity. So when we are speaking about the world, what are the most evident objects which we can have on the world? First, it can be some ordinary objects, in which case we should use Newtonian limit. Like here, otherwise we have stars and we have black holes. So let us see what the torsion by gravity gives in all these cases. So first, let's start with Newtonian limit when we have 2 point masses. And as expected, the Newtonian potential here is given by the ordinary 1/r potential plus some Yukawa type potential, where the relative strength of Yukawa interaction is defined by the parameter eta. I remind you the Lagrangian. So you see the parameter eta appearing everywhere. So this is the relative strength of the massive spin to interaction. And the parameter kappa defines the range of interaction. This is the mass of the massive spin to field. So this is the Newtonian limit. And the interesting thing which we noticed immediately is that in this theory, metric and torsion are such twisted with each other, so that actually the torsion is generated by T mu tensor. And this is very interesting, because we used to think that the source of torsion is only spin density, right? While here we have just C mu, and we already have torsion without adding any spin density. This is a first interesting feature of this theory. Next important object to study is a star. So when we look at the spherically symmetric star solutions, first we as I already said, we see the same number of degrees of freedom as in biometric gravity. So we conclude that we are also ghost-free. And the second thing is, again, on the example of the star, we can see that torsion, a big torsion, is generated by the T mu of matter, as you can see on this picture. And then let's immediately compare with the situation in biometric gravity. In biometric gravity, we have the Einstein screening, which means that on the some distance from the source, the perturbation theory breaks down, which is both good and bad because we have to prove that there exists another appropriate way to describe this theory if we are inside this distance, which is called Einstein radius. But the bad side of this Einstein screening is that it modifies the predictions of perturbation theory. So that the effect of massive spin 2 is like screened. The interesting thing that in torsion by gravity, since there is no denominator of 1 over mass of spin 2 square, there is no Einstein radius. And so there is no problem related to this radius, and there exists no Einstein screening. And the disadvantage of this is that then the predictions of the perturbation theory is valid everywhere outside the source, and comparing these predictions to the results of solar system tests, we have to conclude that this parameter eta, which is the measure of the relative strength of the massive spin 2 interaction, this parameter eta should be quite small. Okay, it's a conclusion, but you might think that if this relative strength is small, then we have no difference between GR and torsion by gravity, but actually not, because even if eta goes to 0, that torsion which is generated by C mu is not small. It stays large. Okay, what is next? Yes. Oh, what I wanted to say, according to this torsion, which remains large, is that actually to feel this torsion, we need to have spin. It's not trivial to feel it, because the usual massive particles, if we are not taking spin into account, they feel metrics, of course. They feel the difference in metrics between GR and torsion by gravity, but they do not feel torsion. The next point in the torsion by gravity world is black hole solutions. Of course, we would like to have black holes. And let me recall you that in biometric gravity, the Einstein black holes are exact bidiagonal, yes, of course, solutions of the field equations, and there exist black hole solutions with a massive graviton hair, which means that there exist black holes which are different, principally different from the Einstein black holes. While what happens in torsion by gravity? We also know that Einstein black holes are exact solutions of torsion by gravity, but there does not exist any asymptotically flat black holes with a linearized torsion hair. Does not exist. We proved. So in our theory in torsion by gravity, we should consider that our black holes are Einstein black holes. And if it is just a non-rotating black hole in rest, it is a Schwarzschild black hole. But it does not prove that our black holes are the same as in GR from the observational point of view, because okay, if it is just a black hole in the rest, yes, it's just a black hole anyway, we don't see it. But if we kick this black hole, it will radiate away many things, which can be measured on the Earth by LIGO, and then we don't know what exactly our black hole will radiate out, because the perturbations of Schwarzschild black holes are different in each theory, and we should study this. And this is what we do now. We started from spherically symmetric perturbations of Schwarzschild black hole, L equals 0. And let me again remind you that in biometric gravity, it was found that if the mass of mass spin 2 multiplied by the size of horizon is smaller than some number, then the Schwarzschild black hole is unstable under spherically symmetric perturbations. And this is related to the fact that there exist hairy black holes, so that in biometric gravity, Schwarzschild black hole, if you kick it, it radiates away a lot, and it becomes hairy black hole. Okay, in torsion by gravity, we don't have a hairy black hole, which could be a final stage of evolution of the Schwarzschild black hole. So, as expected, our Schwarzschild black holes are stable under spherically symmetric perturbations. I'm now studying the non-spherically symmetric perturbations. I have no results yet, but soon I will be able to say something about this stability under general perturbations. But what is important to say is that actually, according to the additional curvature coupling term, which we have in our field equations, there appears a specific denominator which can go to zero and create singularities, really. And the appearance of this denominator actually was predicted already some time ago by Buchbinder et al. And the conclusion is this: the conclusion of this situation is that we need to take the mass of mass spin 2 multiplied by the size of horizon of a black hole larger than this value, square root of 1 plus eta. I remind you that eta is a relative strength of the mass spin 2 interaction. So actually, it means that sorry. Actually, it means that we cannot consider, for example, very small masses of mass spin 2 and of cosmological size, for example. Because if we do it, we will have singularities in Schwarzschild black hole perturbations. So now we know that we should concentrate on the masses of massive spin 2, which are of order kilometer or smaller. Of order, yes, 10 kilometers, 1 kilometer, or smaller also, it could be interesting. If I have time, and if it is interesting, I will say just one more word, because it is a technically interesting thing, is that to prove this stability, the stability of Schwarzschild black hole, we constructed a Zarili-like equation, as exactly as in biometric gravity case, and then this potential V, it is it has some negative part. So here at this picture you can see the potential V in the case of biometric gravity, which is red. You can see it has a negative part, and our potential V, it also has some negative parts. So it was not trivial to prove that the Schwarzschild black hole is stable, because when we have some negative part, it can be unstable if it is negative enough. So this is all my story for today. If you have now any questions, please, you are welcome to ask now or later.
Okay, thank you very much. So we have a couple of questions, even 3. So please, Che-Yu Shen, sorry if I pronounce it incorrectly. Go ahead, ask your question.
Thank you, pronounced very, very, very well. So thank you for the talk. I have a question about the general perturbations. So in general relativity, we can decompose the perturbations into based on their parity. We have actual or parity odd perturbations, parity even perturbations. And I'm just thinking whether this by torsion gravity also allows this separation.
Yes, of course. Yes, of course. We study these two sectors separately.
Okay.
Thank you. Now, Alexander Zakharov, please.
Okay, thank you. Do you hear me?
Yes.
Yes. I would like to ask you about the following thing. So you consider Newtonian, assume that you wanted to distinguish torsion gravity and standard general relativity. You showed that in Newtonian limit, you have some additional Yukawa term. So it means if you wanted to check relativistic effects like pericenter shift or something like this, you have some additional term. It means in principle, you have opportunity to distinguish these two kinds of theories. But later you said that you have Schwarzschild solution. It means if Schwarzschild solution, so it looks like the same solution and there is no chance to distinguish this theory. So that is, could you clarify this issue? Where do you have really differences in this theory to distinguish them in observations or not? Thank you.
Yes. Of course, I have. Of course, there are many differences in observations, and this is why I study phenomenological consequences of this theory. So again, when we are talking about black hole, when we are talking about Schwarzschild black hole, again, even if our black hole is Schwarzschild, it does not mean that the gravitational waves from this Schwarzschild black hole, which we will measure on the Earth, are the same as in general relativity. This is one answer on your question. There are also other interesting things to measure. I'm afraid I have no time to go deeper into the details now.
No, but it's just to clarify my question. So in principle, if you have Schwarzschild solution, you have a Newtonian limit without Yukawa term. In this case, it's how did you obtain additional Yukawa term? Because if you consider, for example, pericenter redshift, if you have additional Yukawa term, you have additional shift due to Yukawa term. So it's quite clear. But if there is no, let us say, additional term, you have only GR effect, famous Einstein effect, pericenter shift. So it's something is in my brain, at least it's something, there is some inconsistent. So.
You are talking about pericenter shift.
Yes, because if you consider, let us say, Newtonian potential plus Yukawa term, you have additional shift due to Yukawa term. It's quite clear due to Yukawa existence of Yukawa potential.
Let's differentiate clearly two things: Newtonian limit and the consequences of black hole physics, and also the periastron precession and other things are not the only observables.
Yes, it's true. But just the last sub question. So is it correct that in principle, so you have no chance to distinguish Schwarzschild solution in standard general relativity and Schwarzschild solution in your torsion gravity? Or no, there is it correct?
If you are talking about
because you said you have the solution as in general relativity without any changes, or there are some case.
Yes, if you are talking about solution, Schwarzschild solution, yes, they are the same. But what you see, you live on the Earth. You don't live on the black hole, right? So what you see is not the Schwarzschild solution. You are what you see on the Earth is what you see on the Earth.
No, that is the reason why I'm saying about pericenter shift or shadow size. That is observable quantity. It's, I'm asking about observations and observational confirmation, or let us say opportunity to rule out these models.
You will not see any difference in which observables did you mention? Could you repeat?
So pericenter shift is famous Einstein effect, and the second effect is shadow size. So, but if metric is the same, so you have no chance to find some differences. But so, it's practically strong relativistic effect.
So you will not see these observables, but you will see another observables. You will see other observables.
Okay, thank you.
Okay, thank you. So the last question by Sergei Vernov, please go ahead.
What is about the speed of gravitational waves? Have you calculated?
Speed of gravitational waves, what can I say about it? When we consider spherically symmetric perturbations of Schwarzschild black hole for example, the fact that we have the really light equation, it, if I understand well, it already means that the speed of gravitation, yes, the speed of gravitational wave is the same as in GR. Am I wrong or not?
I think it depends on whether it's axial or polar perturbations. Yeah.
Why?
Because, for example, in scalar tensor theory, you have or in standard biometric gravity, you have a scalar part, scalar perturbation, which is not in GR. But for example, because of that perturbation, you have instability of black holes in biometric gravity. And in GR, it doesn't exist. So there is, I don't see how you connect some perturbation which doesn't exist in GR to the gravitational speed. See what I mean?
Okay. Okay, I don't know how to answer this question. I should think a little bit.
Maybe another question. What types of function f you use?
F?
Yeah. What if your torsion part, you introduce some function f? What type you check?
Are you talking?
Yes, yes. What is this function?
But no, I say this several times that this is a curvature. It's not a function. It's a curvature of torsionful connection. It's not at all a function.
Ah.
No, no, no.
It is not as f atar.
No,
so
it's like here, for example, when we look at Einstein carton theory, we have f. This f is curvature, just.
It is curvature. Okay, thank you. So you know. Thank you.
Okay, thank you. Maybe the last short question, Mikhail Volkov.
Vasilisa, hi. Can you comment about the status of cosmological solutions in your theory? Because I have impression that your theory doesn't admit de Sitter as a solution. And in your papers, in order to get de Sitter, you need to include additional degree of freedom, which is in the action, you have a term proportional to the constant C6. Without, it doesn't work. And then I also checked that de Sitter is not a solution of your equations. Can you say?
De Sitter as all the Einstein spaces. De Sitter is a solution of torsion by gravity, but you need to add the cosmological constant explicitly in the Lagrangian.
Exactly. Right. Okay. Thank you.
Okay, thank you very much.